In the very first episode of the Haskell Unfolder, we talked about the unfold function and contrasted it with the more widely known fold or foldr function. And we did that on lists. So in today's episode, we want to connect to that topic and talk about folds and unfolds again, but not only on lists, but on other data types as well. And we are going to discuss sort of the generic construction that leads to the generic pattern of folds and unfolds.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them. And yeah, we're going back to episode 1 today for a very special reason, because we are 1 year old today. This is episode 24. This is 1 year of Haskell Unfolder, and hopefully there's going to be many more. Now, we thought it might be nice to celebrate a little bit, so we're going back to episode 1, sort of close the circle, but also we thought it might be nice to have some Unfolder merch. So if you wanted to show your love for the episode, yeah, we have some. On the front is the Unfolder logo, and then at the back we have a typing rule for the generic unfold that we're going to talk about today. And there's also a mug. So yeah, if you're interested in that, feel free to get one.
We are not
making money
earning
from this. Yes.
We are not earning from this. Only Spreadshirt is earning from this.
Yeah, it's just
not.
fun.
Yeah. Okay. Let's get started. So let's look at a simple data type of binary trees. To have a simple data type, but one that is not a list. And I've given a definition here. This is a binary tree with labels or elements in the leaves, no elements in the node. And this is an example tree, which is just sort of like a four leaves and written in a balanced way. Now, fold and unfold are what's called recursion patterns or recursion schemes. And the idea is that they're capturing a particular way of doing recursion. And it's a general principle that recursion in functions often follows recursion in data types. So it's perhaps not surprising that the first step to this sort of generic construction is to look at the data type that we want to somehow traverse. And in this case, that is our tree data type, and do something with the places in which this data type is recursive. Right? So, and I'm talking about these two places here. In the node, we have these two subtrees, and these are recursive occurrences of the tree data type that we're defining. So what we're going to do is we're going to define a new data type, which is called treef. Treef, I mean, the name is arbitrary, of course, but the idea is that the F is for functor. I'm going to talk more about this. And treef has the same parameter A that the tree data type is, but it has one additional parameter R. And the idea is that we are going to abstract from the recursive positions of the original data type and use this R instead. Otherwise, the treef data type is going to look exactly the same as the original tree data type. Of course, we cannot make it look exactly the same. We have to pick different names, but I'm just going to call the constructors leafF and nodeF. So nothing changes in leafF because there's no recursion there. And in nodeF, we're not going to get tree A, but we're going to get RR instead. And again, I can derive show for this so that in principle we can show these values. Now, I can give an example treef as well, something like a treef int. Now I have two parameters, so like say the elements would still, like the thing in a leaf would still be an int, but for R I can now choose, right? So for example, one option is I can say I want to put strings in the recursive positions. Right? So I could write something like node F, and now I have to put two strings there because now I'm in the node case. The node case has two R's in it, and we have instantiated the R to string, so I can do something like Haskell Unfolder, or perhaps I should have been writing happy birthday or something like that. And But an interesting instantiation is the one which gives us back something which is very similar to the original data type, and that is if we instantiate the R with tree of A, because like we've abstracted from this, but if we instantiate the R position, the R parameter with tree of A, we quite obviously get something back which is isomorphic to the original data type, right? So there is an isomorphism between tree of A and let me see if I can do this, right? And tree F of A of tree of A.
And just to be clear, an isomorphism means that every value on the left has a corresponding value on the right, and every value on the right has a corresponding value on the left, so that they're a one-to-one correspondence.
Yeah, so for the example tree I've written before, the corresponding one would be simply the one where we are replacing the topmost node with node F, and everything else stays the same. Right. But we can also more generally witness this isomorphism by just defining conversion functions that go in both directions. And I'm going to call the one that goes from tree A to tree FA, tree of A. I'm going to call that one pull, because kind of like it looks at the top level constructor and sort of like pulls it out and like shifts it into this different data type tree F and makes sort of the top layer explicit. That's the idea of why I'm calling it pull. And pull of a leaf is just going to go to leaf F and not do anything to the argument. And pull of node LR is going to give us a node F of LR. So it's really a rather, it's almost boring, right? I mean, it's very, very straightforward. And the other direction I'm going to call push, and it is equally trivial, right? Because here we simply go from leaf F of X back to leaf of X, and we go from node F LR to node LR. And it is also very obvious that these are actually inverses, right? Like if you apply pull after push, you get exactly the original value back. Now, this construction that we've now done for tree, we could have equally done for many, many other data types, like for lists or other kinds of trees, or a data type for expression, some AST data type, whatnot, right? I mean, as long as it's a data type and it has recursive positions, we can in principle do the same construction. And because we can do the same construction for many different data types, it makes sense to capture this in a type class. So let's try to do that. Let's define a type class that I'm going to call rec for recursive, because we are trying to identify the recursive positions of T. And well, I mean, T is now playing the role. I mean, in the end, we want to define an instance of rec for tree of A, right? That is the idea. That's where we want to go. So T is playing the role of our tree of A, but we need to relate tree A to tree F AR. So we need to establish this relation between a type and this functor, as it turns out to be, which abstracts from the recursive positions. And we are doing this by defining an associator type. So that's like a type family, but it's included in a class. And I'm going to call this functor of T. And because it has one extra parameter, the kind of the result kind of this functor of T is not just a plain type, but is a parameterized type. Right? This is of kind type to type. And then the type of pull is going from T, that's the tree A here, to tree F of A, so that's the functor of T. But then functor of T gets one additional parameter, and that is instantiated to the original data type again. Right? So functor of TT. and push is going the other way around, functor of t to t. Okay, yeah, now Haskell language server is complaining at the moment because I have pull and push also defined outside of the class, but we can fix that because we can now define an actual instance of the class where I'm saying that the functor of tree A is actually tree F of A, and then I can simply move pull and push into the class and everything type checks again. Okay. Now, what have we won? Well, the idea is that now for everything, for every type that is a member of the rec class, we can actually define something that is a fold and something that is an unfold. And let's start with a fold, because I think folds are more common and they're a little bit easier to grasp. The idea of a fold is that we want to go from a value of this type t, that we are considering, this recursive type t in general, to some other result type r. That is the end goal. And we want to do that by providing some information, but ideally information that can be written as a non-recursive function. That's the idea of a recursion pattern, that it captures the recursive part and you only have to do something that is non-recursive. And this function that is needed as an argument in this generic thing is simply something of type functor of t, where the recursive position is instantiated to r, which is the result type of our fold, and is going from there to r. So this is the type of the generic fold, but of course we need a class constraint that t should be in the rec class. Okay? And now if we go about how to define this, we can mostly be guided by the types, right? So let's start by just assume we have an x which is of type t and see what we can do, right? So one of the things that the rec class gives us is that we can apply pull. We can apply pull to this x. And if we apply pull to x, what do we get? Well, we get a functor of t in the general setting, right? And in our tree setting, we get something. Perhaps I should actually let me just split and put the class definition so that it is visible, right? So that we have the type of the class visible in the upper window here. This is so the type of pull in the general setting. And now we are at a point where, well, we would like to turn this into something of type functor of tr. Why would we like to turn this into something of type functor of tr? Because we have this argument to fold here, which, by the way, is often called the algebra of the fold. So I'm going to give this the name alg here. And if we have something of this type, we can simply apply this algebra to it, and then we are at type r, which is the type that we need, right? So the important missing step is that we have to go from functor of tt to functor of tr. But now functor of is already sort of named functor of. So if functor of t is actually a functor and we have a map function over it, right, then we can change the parameter of this by applying some function of type t to r. So let's do this by actually requiring in the rec class as an additional superclass constraint that functor of t is actually a functor.
You mean functor of?
Functor of, yeah. And now Haskell is complaining that tree f is not a functor right now, but that is easy to fix. We can simply derive it. Note that this is for tree of A, if we were to derive functor, we would get something that operates over the elements of the tree. But if we derive functor for tree FAR, we get something that operates over this R argument and leaves the elements alone, right? So it's something that allows us to change what is in the recursive positions. So now we really
There's
just
a
have
question
to...
here that actually might be useful to bring up, because other people might be wondering the same thing. So are there implicit parentheses? Is functor of t is a bracketed like this?
So I mean, the answer to that is yes, but I mean, like always, sort of like function application on the value level and on the type level, and Haskell is curried and associates to the left. So so if you like to think about it being like having extra parentheses like this, that is perfectly fine, right? But they are not needed. You can omit them, but yeah, if that helps, I can put them there. So so we want to fmap something over this pull x, so that we get a functor of tr, and we need a function from t to r, right? But if you look at the type of fold, we are just defining a function of t to r. So if we recursively, and this is like, I mean, it's not surprising that if we are defining a recursion pattern that it is recursive, if we're recursively applying fold alg over this inner thing, right? Sorry, now I'm getting one more like this. Then we are at then we have the type that we wanted, and then we can apply alg to the whole thing, and that then goes from functor of tr to r, right? And so now this I can copy into the definition. So actually I don't even need to like pick up the x. I can simply write it as a composition. I can say this is alg after fmap fold alg after pull. Okay. I know this is still a very like abstract way of defining it. So let's look at an example. So let's define an actual fold on a binary tree, and let's, as a sort of like first example, just take a binary tree and do a traversal over all the elements in the binary tree and collect them in a list. So let's define something that's called toList, and that is taking a tree of A and is giving us a list of A's. And the idea is that we can write this as a fold. And what we need here now is something of type treefa list of A, so where the recursive positions are already lists, right? And then we have to turn that into a list.
So the recursion has been taken care of, right? Which is kind of the point.
Yeah, that's what we wanted, right? So here we can do something like lambda x case x off, and we have to look, is this a leaf? If this is a leaf, then we are producing sort of the singleton list that is just containing this one x. And if this is a node f of L and R, now L and R are already lists, right? The recursive results. And we can simply concatenate these two lists. And then let's try this out. Let's try toList of example tree. And we get the list that contains 1, 2, 3, 4. Okay. Now, another example is like if we want to produce some textual representation. I'm not quite going to sort of like do the show class, but let's define a function render that takes a tree A to a string, and we are going to require that the elements are in the show class. And again, I'm going to define this as a fold, and I'm going to say what are we going to do in the leaf case? Well, in the leaf case, we're just going to show the element that is in the leaf. And in this case, we are getting two strings already, right? The results of recursively applying render to the left and the right subtree. and we have to put these two strings together somehow, and there are various ways of doing this, but I can just, for example, put some sort of symbols around everything to give some impression of the nesting structure. And so if I do render of example tree, then I'm getting a string that looks like this. Okay? Good. So now, what about unfold? Right?
Before we go to unfold, perhaps there's one comment from Travis, which might be worth pointing out. That Edward commit calls pull project and push embed.
Yeah.
So
it's a good point. I would have said this. I mean, everything that I'm doing is very, very similar to what the recursion schemes package on Hackage is doing, which is by Edward Kmet. There are just minor naming differences. And indeed, that is one of them. That what Travis just mentioned. So, instead of pull and push, Edward is using project and embed, and also there is not one rec class, but there is a recursive and a co-recursive class, and one contains only the project function, the other contains only the embed function, But these are minor differences. If you understand what I'm doing in this episode, then you will also understand what's being done in recursion schemes and vice versa. So that's fine.
There's one other comment that where's the accumulator in the fold? I understand we are not doing classic fold R, but it looks like the accumulator is completely removed.
So this is a bit of a terminology question. But I mean, so first of all, I mean, I don't really like to call the argument of fold R an accumulator. I typically only use accumulator in the context of fold L, and what we are doing here is fold R. But I think what the question actually means is that, for example, if you look at the type of fold R on lists, it is A to R to AR to R to list of A to R. And let's actually do the same thing for lists. So I mean, now that we got the question, before we go to unfolds, let's do this thing for lists. So if we want to make lists an instance, we also need a list F type. So I think I have this. So I cannot use the built-in syntax of lists for my list F type, so that's why it looks ever so slightly different, right? So list F has a type A and a type R, and then it has a constructor corresponding to the empty list and a constructor corresponding to cons. And because we have a recursive position here, we have an R here, and then we can make lists an instance of the type class rec, just as we are used to. And if we look at the type of fold that we are getting for this, right, for our generic fold, then we get list F A R to R to list of A to R, right? But now, if you look at the structure of list F, it is essentially structurally equivalent to either it is nil F and that contains no information, or it is cons F and that is a pair that contains essentially a pair of an A and an R. So a different but equivalent way of writing fold would be not to use list F, but to use either the unit type, or I could also use maybe either the unit type or an A comma R to R. Right? And now, if you have a function that goes from an either AB to an R, you can equivalently provide two functions, one that goes from an A to an R and one that goes from a B to an R. So in our case, we could rewrite this one as saying, what if we have a function from unit to R, and if we have a function from AR to R, then that is still essentially the same. And now if you have a function from unit to R, that is the same as having just an R, essentially, because there is just one value of the unit type. And if you have a function, oh, here I should have put parentheses, sorry. If you have a function that goes from a pair of an AR to an R, you can uncurry it. And so this one is also equivalent. And now you can flip the two arguments, right? So in the end, all these types amount to the same thing, right? And similarly, with a similar construction, if we have the fold for our tree data type, so if we have tree f a r to r to tree a to r, and you do the same kind of simplification, you could come up with a equivalent definition of fold on trees, which basically takes a function for the leaf constructor, which takes an a to an r, and a function for the node constructor that takes an r to an r to an r, and then goes to tree a to r. So these things are equivalent, but like phrasing them within this extra functor data type makes the correspondence, the generic correspondence between all these different data types much clearer.
Yeah, so just to close this subject, and then let's move on to unfolds, because we're good. But we are, so although we are talking about a much more generic or much more abstract or much more general concept of folding, for the specific case of lists, we are in fact doing classic fold R. Right?
Yeah,
it points down to the same thing for lists, but it's just more general.
Right. I mean, if I wanted, and now I know that you said I should move on, but if I wanted, I could give like the original definition, right, on lists. I could write as fold of lambda x case x off, where in the nil
arguments.
Where in the nil. Sorry.
You're going to want to give some arguments, I guess.
Fold cons nil, let's call it. Where in the so in the nil case, I'm hearing some weird beeping sound, but I'm not sure where it's coming from. Sorry. What do I have to do now? Now I'm confused. Where in the nil f case, I'm going to just return nil, and in the cons fxr case, I'm just going to return cons xr. This is this makes the relationship between the original fold R and fold precise. Okay, so yeah, now now we've still not actually even talked about unfold. So let's look at a generic unfold as well, so that we have at least done that. But I'm glad that I'm getting questions, so that's, don't get me wrong. So if we want to do an unfold, the idea is that it's just going the other way around, right? I mean, sort of like in the theoretical background, the word for this is dual, and that primarily means that you flip the directions of certain arrows around. So the idea of unfold is that rather than taking something of type T to R, we are going from something of type R to T, and in order to go from something of type R to T, we need something that goes from type R to functor of TR. So, and the argument to unfold is often called a coalgebra, and the definition is also sort of interestingly reversed. So here we start with an R, and that is already in the right shape to apply our coalgebra to it. So we can start by applying coalg and then compose that with something. And then we have a functor TR. And again, we can fmap the function that we are just defining over it by fmapping unfold of coalg over it. And this is a temporary type error. And then what we have here, what we have here needs to go from functor T t essentially if we did this right to t, and we can just use push in order to do that. So like the order of the three functions is reversed. Pull is replaced by push, but otherwise it's mostly the same.
So I find this very beautiful, right? It's the duality between these two functions is so explicit here.
Yeah. So yeah, let's try to define a function. We don't have much time left, but to at least see one example of this, let's define something that builds a tree. Let's say we are taking a depth, and we're taking an element to put in every position, and then we want to build a tree of that type. So that is our d and our x, and we basically want to build a complete tree of that depth where in every leaf there is this x. So let's say we have if d is we are going to define this as an unfold, and we need this coalgebra, and we need to pass it the sort of initial seed value, which is the d, and let's call this step, and step if it takes this integer, and if the integer is less than or equal to 0, then we want to produce a leaf, and if we always want to put an x into the leaves, and if I is not greater than 0, is not less than 0, then we're going to produce a node. And now in the recursive positions, we have to put two integers again, which are sort of the new seed values for the left and the right subtree. And because we want to create something of depth d in total, or I in total, we are going to subtract 1 from the depth and call that in the left and the right subtree. And again, the recursion is being taken care of by unfold. Step is not recursive, right? That is the achievement. By using these recursion patterns, we are extracting everything that actually does the recursion into this one function. And let's try to call this as well. If I build a tree of depth 3 with, say, characters x in the leaves, and I evaluate that, then I get something which looks a little bit ugly, but fortunately I've previously written render, so I should be able to call render on the result of this, and then we can see that it looks as expected, right? Okay, I would have loved to show more, but I think we're basically out of time, and perhaps there are even more questions.
No.
I can make a couple of small final remarks without going into too much more detail. So one area where I think unfolds are often relevant are sort of if you have games or anything that looks a little bit like games, sort of like games in the wider sense, you have something that can be completely described by some kind of state, right? And then you have legal moves that you can make in a particular state, and you essentially have a function of type f that takes you from a game state, and then it makes a move, and it takes you to a new game state. And you can imagine creating a tree out of that has sort of game states in the nodes, and then is branching widely, where you have like one branch for every possible move out of that state, and so you can unfold the whole game, right? All ways to play the game by essentially calling the generic unfold on this function, right? Which is not a recursive function, but on effectively on this function, and that is like sort of a very wide class of unfold-like functions, which I think are very useful in practice.
Yeah, for example, but like just to give an example, which is not a game, the Cabal solver, dependency solver, works in exactly this way, right? It produces a big tree
Yeah.
of where moves are picking packages. I'll leave a link to a blog post
You
that talks about this.
you can see dependency solving as a game, yeah. But I mean, it is indeed it is a similar situation. If you have some sort of optimization or search space problems, you can try to unfold the solution tree and then like afterwards traverse it in some ways by doing other recursive traversals over that tree. And of course, a key point for a scenario such as this Cabal dependency solver, and also often for the game scenario, is that you don't actually want to compute the whole tree, so that you are sort of fundamentally relying on laziness at some point. You only want to explore certain parts of it in the end. But that can all be done in this style, right? So that's a good option. And perhaps another sort of remark I should still make, because we've already mentioned recursion schemes package, is that I think the fold and unfold are sort of, I think, the most important recursion schemes there are. There are also widely known as katamorphisms and anamorphisms. Kata from Greek kata, the preposition kata meaning down, because it is folding, it is destructing something, like tearing something down. Anamorphism from Greek ana for up, because it's building something up. But there are many, many other variants of these recursion schemes that can also be defined just by having essentially an instance of this rec class that we have done, and by plugging push and pull and fmap and whatever together in slightly different ways, or keeping track of some additional information, and that leads to a whole wealth of other related functions, which are all defined in the recursion schemes package. So you can look at them there. But yeah, I think we can probably leave it at that, I guess. So
I think so. So yeah, so thanks everybody for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And feel free to leave any comments below. As always, we'll leave the chat open for a few more minutes if there's any final questions. And if you want to have questions after the chat closes, then just leave them in the comments. Also, yeah, thank you not just for this episode, but also for staying with us for the first year. This is not the end. This is just our first milestone. We're hoping that there's going to be many, many more. So yeah, hope to see you guys in the next one, which I guess will be in 2 weeks.
Yep. Thank you.